What is molecular dynamics simulations? So MD is one important tool in the biological sciences, and it is being used a lot these days just to understand the atomistic details of the biological systems. It basically calculates time-dependent behavior of the molecular system, and it provides detailed information on the fluctuations and conformational changes of the proteins and other biomolecules, which may be impossible to do with the real experiments in the laboratory. So basically, this provides a type of a computational microscope to you, that understanding the behavior of atoms in real situations. So on the right, you can see that in a system, when a atom which is having some potential energy comes and touches the surface, it transfers that energy, and suddenly there is movement which is observed in all the atoms. So basically there are two things. One is the atomistic uh, locations which are being changes. That means that their state is changing according to time. And others are the thermodynamic properties, such as there might be some changes in the energies. So all these will be taken care in the process of molecular dynamic simulations. So basically, MD simulations is a computer simulation. Simulation means trying to mimic some process. So it allows to interact certain amount of molecules or atoms in a system for a particular period of time. So we can basically set the time for that. We want to simulate our system. So it basically provides an interface between laboratory experiments and theory, right? So this is also referred to as virtual experiment. And a recent term which is being coined for molecular simulation is the computational microscope for molecular biology, because it can actually tell you the details at the atomistic level, what are the processes which are happening, especially related to the molecular motions of the system, biological system. So molecular dynamics has several applications in studying biomolecular systems, including protein stability, conformational changes in the proteins, protein folding, and other mechanisms. Especially in this case, we are going to study the drug design application, where we checked the protein ligand binding in the previous experiment. So we'll be confirming whether that pose is retained uh, in a real situation when we subject it to the dynamic behavior using molecular dynamic simulations. So here is the slide again, which shows the binding of a drug molecule, which is dasatinib, uh, which binds to its drug target called as SRC kinase, which is implicated in breast cancers. So this is an established drug, and through molecular dynamic simulations, this movie is basically a snapshot of several trajectories which are saved during the molecular dynamic simulations. And it shows you the actual behavior of the drug molecule and binding of the drug molecule ultimately at the binding site or active site of this protein. So in the process of molecular dynamic simulation, there are several steps involved. So initial requirement is the structure, or the initial structures of the protein and the ligand, of course, we are trying to simulate here. So we should have the initial positions, which are referred to as R, and velocities, which are V. And these will be dependent on the potential energy which is exerted on the initial structure. So then for the computer, in order to understand what is the structure of the molecule, so there should be some topology file which we will provide to the system so that it can understand it. And then there is something called as force field, which is basically a way that how we can basically a mathematical expression to calculate the potential energies of the molecules, whether it can be bonded or non-bonded terms. So combining these initial things, you will compute the forces on the system and then try to solve the Newton's equation of second law of Newton's second law of motion, right? Newton's second law. So this molecular dynamics is completely based on solving the Newton's equation of motion. So these steps can be repeated again and again. It depends how long we want to simulate the whole system. And ultimately, we get the output in terms of position, velocities, and energies. And from these outputs, you can actually carry out the analysis. So here is the global MD algorithm, which works in this manner. So first, it will require the input of initial condition, that is, will need some initial structures which are having some potential interaction in terms of V. That is the function of atomic positions, such as the 3D structure of the protein and ligand which we are providing to it. And they will have some positions initially, that is X, Y, Z coordinates, because they are in 3D conditions, so which are referred to as R in this case, and the velocities of all the atoms in the particular system. So we have four major steps here. Step 2, 3, and 4, they can be repeated again and again, depending on the time period which we are simulating it for. So second step is computing the forces on any system. So basically force, it is a negative gradient of this potential energy which is present in the molecule. So basically we are summing up all the forces. So we have to calculate the force on all the atoms which are present in a particular system. And further, whatever the forces are available, these forces may change the configuration of the particular state. So this will update the configuration, and this configuration ultimately requires the calculation of Newton's equation, which looks something like this. So basically, Newton's second law is force equal to mass into acceleration, which can be representative of this form, that is force is equal to mass, and this is the velocity, time change of velocity, which is acceleration, of course. So this calculation will change the state of this particular molecule. So ultimately, this state can be outputted in terms of positions, velocities, energies, and other thermodynamic parameters. So then these three steps are repeated and again, and this will ultimately give you a trajectory of motions and energies, which can be analyzed. So how this force is being exerted due to the potential energy of the molecule. There is a way to calculate that, and the way is by using so-called as potential energy function, or also known as the force fields. So force field, they have two major energetic terms which can be measured mathematically. So we have one that is bond energy terms, which includes your bond stretching term, angle bending, and dihedral term. So they have these mathematical equations here. So for a particular a set of atoms, for example, two atoms in this case, you may observe the bond stretching behavior, angle bending behavior, or rotation around a bond, which is dihedral term. So all these are represented in terms of mathematical equations here. And you are familiar from the last slide from yesterday that we have something called as van der Waals term, which is the representation of Leonard zone potential and electrostatic term combined with the hydrogen bond term. These are the general terms which are non-bond energy terms. Basically, these atoms in the system, they are not directly bonded, but they are in very close proximity, which exert these forces. So you can, by using all these equations and summing up all these forces, we can obtain something called as potential energy, right? Which will further exert some force on it. So all this will be circulating in a kind of a cycle. So what are the practical steps in molecular dynamic simulations? The very first thing is topology preparation for your molecules, that is protein and the ligand, which we will obtain from the molecular docking experiment done yesterday. And next one will be generation of simulation box. So this is generation of a simulation box. Here you can see uh, the simulation box. Further solvating the system and neutralization. So basically we are generating a simulation box, putting our molecules into it, such as this protein, and further these sky blue color are the water molecules, and these large spherical atoms, they represent the neutralizing atoms. They can be negatively charged chlorides or positively charged sodiums. They are just used to neutralize the system in case our system has some charge. So because the computational simulations, they work under the neutral charge. So next is energy minimization. So you need to lower the energy, overall energy of the system, so that there are no clashes which may further during the actual simulations, they may integrate into, or sometimes your system will explode if you have some clashes in your system. So it's important that you lower down the energy, overall energy of the system first through energy minimization. Next is equilibrating the system by using two ensembles, which we have NVT and NPT ensembles. So you'll provide some parameters there to equilibrate the system. This is basically some kind of calibration of the system before running the actual experiment. So you need to calibrate by using the equilibration um, under different ensembles, that is NVT and NPT. Then running the simulations and production run. Here you'll decide that how long or how much time we want to expose the system to, and you can determine through parameter file. And finally, the analysis part. So Gromacs involves several file types. So it is important that you understand these file types. The first one is top file. So this is basically a topology file which will contain all the molecular details. And whenever we proceed with every command, so you have to just update this topology file. Second one is a GRO file, which is the coordinate file, which will contain XYZ coordinates for your protein and ligand. MDP file, which is molecular dynamics parameter file, where you will define the parameters. An index file where you can define what are the important sections in the index which you can define for the system. You have TRR and TPR file, which are basically binary files which are not human readable, but they can be used for the analysis. EDR file for calculating energies, log for tracking whatever is happening in the simulations. Then the CPT or the checkpoint in case you uh, in case there is some error or crash of the simulations, you can start from previous checkpoint by using these files. So these are some of the file types, and we'll check step by step what are the files which are being produced. So you will need um, the software called as Gromacs, which runs on command line. So we need to shift to Linux platform for running this Gromacs software. Well, then you need VMD for visualizing the trajectories. And of course, you need protein file and ligand file. And most of this tutorial is based on the Gromacs tutorial from MD tutorial. So I have provided the link. You can go back and check the details there. And finally, we'll assess the results where you'll see the energy minimization, temperature and pressure profiles of the system, whether everything's going fine over there. and ultimately RMSD and RMSF profiles along with the radius of gyration of the system. So we'll try to produce these results. So with this, we'll move to practical demonstration. If you have any questions, I can take some questions now. No questions? All right. So here I have installed this virtual box, and inside that I have installed uh, the Linux program, Linux platform, which is known as Fedora. Okay, so one important thing which I just missed, sorry about that, that is preparation of the molecules. So for your guidance, I have again made this protocol file. So it involves stepwise demonstration that are involved in this analysis uh, and in this experiment. So this will be provided to you. So first part is topology preparation for the protein and ligand, right? So for the protein, the topology will be produced by the Gromacs software itself. But the topology for the ligands, they are not usually available in the Gromacs. So you have to generate the force field parameters separately for your ligand. So if you remember yesterday, we had generated a protein and ligand complex. So here you need to treat them separately. You have ligand that is in Mol2 format. You have a protein in PDB format, right? So first thing we'll do here is generate the topology for the ligand here. So for that, you need to uh, go and check for the program Swiss param. There can be different um, platform or different programs which can be used to generate topology of the ligands. So it depends totally on the type of force field which we are going to use. In this case, we are using charm force field. So this is a Swiss Bioinformatics Institute resource called as Swiss param, which will generate ligand topologies for the charm force field. So you can go to this Swiss param website, choose your ligand. So I will just give me just get the path from here. So already set there. So I can choose this lig molecule, open and submit. So make sure that your molecule which you are providing, it has all the hydrogens attached to it. Otherwise it may show some error. So you have to click that link and just save this file, which is um, ligand.zip. So so sometimes it doesn't download from the Chrome. I'll shift. So here I'll copy. Okay, so it shows it is harmful, but I'll keep the file anyways. And it will give me this zip file, right? So you can extract this zip file. So I've already extracted it here once. So these are the files which are provided by Swiss param. So what are these files? These are the files which are used by different softwares. So in our case, we'll be choosing two important files from here. That is, one is the coordinate file, that is lig.pdb, which will be converted into lig.gro format, that is the Gromacs file format. Um, and then another one is ITP file. So what is this ITP file? Basically, it contains the parameters for um, the atom types, pair types of the system. Basically, this is the way that the force field recognizes different atoms in the ligand molecule. And then you have all the specifications and the parameters for uh, your ligand present in this particular file. So this is a force field file for your ligand, which is not available in Gromacs. So we'll be copying these two files to our main directory where we are working. And now I have 1, 2, and 3 files. One is protein file, PDB file for the ligand, and ITP file for the ligand. Along with this, we need several parameter files which we require for running the simulations. I have already copied it there, so I will try to provide those files uh, altogether to you. So basically, we need to copy all these files to our working directory that is in the Linux platform. So I will go back to the Linux, so which is, yeah. So this is the Linux platform, which is running currently under the VirtualBox. So I'll go and click on files just to show you that where I have saved my files previously. All right. So currently I am in this home directory, and under home, I have made this next gen helper. And then this is the folder where I have copied the files. So basically, okay. So basically, this is the protein PDB file which we imported. This is the ligand PDB file, and this is the ligand ITP file, right? So these are three files which we imported from the Windows system to here, right? And apart from that, you have energy minimization parameter file. For ions, we need this file, that is ions.mdp. This is for running the production run. And these two files are the parameter files for NVT and NPT ensembles. So we'll try to learn them when the step comes one by one. So these are all files, they are required in the present working directory, right? So now I will open the terminal. So basically you need some knowledge of running command line system. So if you are not sure where you are in the terminal, I can put this command, that is pwd. It will show me under root, I am under the home directory, and I am working in my profile that is under home. So I will put ls to list everything which is present in this home directory. Basically, it is uh, the same thing which you see here, right? Under the home directory, you have all these folders here. You can see the same thing in the command line prompt, correct? So I will go and find this next gen helper where my files are lying. So I need to change directory to next gen helper directory and hit enter. So for your information, right now, you see before this dollar sign, there is next gen helper. That means I am already into this directory. So I'll again put ls list. It is inside there. Now I can see all the files which were present in the next gen helper. So this is basically the folder where we are going to perform our simulations. So other two file, you will be wondering, these are just for the reference for the analysis, because this is demo purpose. Simulations, they are computationally exhaustive, they take time. So these are for the reference. We'll be using these for the analysis. So let's proceed with the first step. So I will clear everything and show what is in there, right? So you can go and navigate to this file here, that is for your reference. So topology preparation for the protein is the first step. So remember that topology preparation is the first step. In this, what we are going to do is we are engaging one important tool, that is GMX, PDB to GMX. Basically, let's try to understand this command here, which we'll be using for um, our study. So first one is GMX, PDB to GMX. This is the tool which Gromacs will engage, and -f is input for this tool, and input will be the protein file which we engaged from there, right? And output by -o flag, and we'll name the output as protein underscore processed dot grow. So now you can see that what will be the change which will happen here. It will convert the PDB file to Gromacs file, correct? And then some other flags are required. These are optional. So ignoring hydrogens means you can add the ignore the hydrogens from uh, the PDB file, and basically let the force field add the hydrogens by itself. So this is important. Sometimes if you don't use this flag, you will get some error. So use this flag. And then specifying that I'll be using SPCE model for the water. Basically, this is a computational model for the importing the water molecules. So simply just to save time, ideally you should be writing and exercising it. For saving the time, I'll just copy this command and paste it in this prompt here, right? And see what happens. Okay, so now it will ask me to select the particular force field. All right. So here I have a list of force fields which are available, which are inherent uh, to Gromacs. So these and all are the lists. If you remember, I had put one. Remember, I had put one folder there, which where I downloaded from external source this charm 36 force field, which is the latest charm force field. So I'll be using this one, which is often presented on the first. So basically, if you want to choose Ember 3, you will put 2 here. If you want to go with Gromos 96, you will put 10. Put the number here, right? I'll go with the 1, right? OPLS, you have 16 and so on, right? So in this case, I'll be choosing 1 and hit enter. So now it will calculate some parameters. Basically, what it will do is it will convert the protein PDB file into Gromacs file. This is nothing but coordinate file which Gromacs reads. So this coordinate file includes your XYZ parameters. So let's see once this step completes. So still it is writing the topology file. So we have to wait what and all is happening until it completes this step. It may take some time. It's taking more than usual because I'm running too many things on my system. It becomes slow. If you're running it on your Linux machine, it will be much more faster. So till this point, you have any questions I can answer? The manual for Gromacs, you mean? It is available on the web for free. You can access, you can go to the Gromacs um, website, official website, you'll get the manual there. And for the tutorial, I have provided the link here, right? So you can go and check this. I'll provide this PPT as well. Okay, so now you can see uh, it was writing the topology file and it has finished. Once you finish some job here, it will give you some flags. Sometimes it's very funny. So cut it deep and cut it wide, and so these kind of flags. So this is one type of confirmation that okay, your job has finished. So let's see what has happened in the file section, right? So previously we had some files, but I'll draw your attention to important files which have been produced: 1, 2, and 3. Okay, these are the new files which were obtained after running the first command. So what is this protein processed grow file? I'll use my terminal to access this file. So I will engage VI editor, that is kind of text editor, and we'll type in protein processed grow. And here you can see what are the contents of this file. So basically it will give you the residue number, that is 39. So this protein starts from 39th residue, and the first residue is serine and it contains these many atoms. How many? 13 atoms. Okay, so these are the atom numbers. These are the residue number and name. This is the atom type which is specific to every force field. And these are the XYZ coordinates. And these are total number of atoms in the system. Correct. So this whole file is full of this coordinates for your protein, right? So this is the protein file. So next is your position restraint file. So basically we need it for equilibration steps. And what this file contains is basically we'll try to put some restraints in this form. For every atom, it will produce X, Y, Z coordinates. Basically, this file is required for the position restraint. And another important file is this topology file. So I will go and check what are the contents of this topology file here. So here you can see this will include some important parameters. So first thing is force field parameters. And here I was using charm 36 force field. So this is in the form of ITP file. It will engage that force field file to process to further steps. This is the topology file. Okay, so this is acting on the protein, so it will include the protein chain, right? And then you can scroll down. These are the atoms and their particular details of everything in this topology file. So I'll jump directly into the bottom and show you some important things here. So basically this one is for the position restraint. So this is position restraint ITP file, which is this one for the protein. It is already included in the topology by default. And we need to add the position restraint for the ligand. We'll do that later. All right. So basically it will tell you that what are the system which is in the system, what are the molecules which are present. So this section is important, molecules. So here you will see currently protein chain A is present, only one molecule is present in the system. So that's about the topology file. We quit it. And we are ready for the next step. So first step was completed successfully, that is generation of Gromacs file from the PDB file. And additionally, position restraint file was generated, this one, and a topology file was generated, that is this one, right? So we already had generated this um, uh, this ligand PDB file. So next step is convert this ligand PDB file into the grow file, right? Because Gromacs, it likes to work in the grow file, right? It understand PDB also, but it is ideally you need to convert to grow file because we want to build the complex later. So what I'll do is I'll just copy this command from here, paste it here, and there you go. So what has happened is it will produce ligand processed this file. So this has been produced. Okay, so what are the contents of this file? If I want to see, I will again go to VI and type in the name of the file which I want to open, hit enter. And now you can see what are the contents of this file. So you have this lig, that is the name of the ligand atom. These many atoms are present, and these are the X, Y, Z coordinates for the ligand atom. So totally 63 atoms are there. So what we need to do is, next step is building the complex. That is, we need to import these coordinates, that is all these coordinates, into the protein Gromacs file. Remember, in the first step, what we did is converted a PDB file into Gromacs file. So this is just for the protein. We need to add the ligand also, right, in order to simulate. So we will use these coordinates and put into the protein Gromacs file. So simply I can so remember, these are the number of atoms which are present in our ligand. So I will copy them. Okay, so it can copy up to 35 in one go. So we'll do it again. Copy, close this file, and I will go to protein process to grow, right? This one, shift plus G, that will bring me to the bottom of this file, and I'll put insert in order to insert something from my keyboard. You can see this flag comes here, that is insert. Now it is in insert mode. Hit enter, and you need not to change this average, that is the origin of this particular coordinate file. So I'll leave it, right click and paste. So now you can see 35 atoms of the file, ligand file, have been imported here, but there are some remaining because there are total 63. So I'll escape. WQ means save and quit. I will again go to the ligand file, scroll down, and copy the contents from 36 atom, this one, right? So up to the 63 atom, right click and copy. So you be careful that you don't need to copy this bottom line, only up to the atoms. So I've already copied it. So quit without saving. Again, you can use upper key to go to the previous commands which you have used, like this, right? All previous commands will be coming. So I want the second previous command, that is view the protein file again. Go to the bottom, insert, and paste the remaining atoms here. All right. So now you can see that 63 atoms have been changed. So these were the up to 766, and these many atoms were for the protein. And after that, we have built the complex or coordinate file for the protein. These are the protein atoms and these are the ligand atoms. So now it is a protein ligand complex. But remember, one more thing which you need to change is change the atom numbers here. So basically you can copy and calculate how many are there plus 63, right? So these are the atoms of protein plus 63. So 11715. So you need to change this number, right? Change this number to 11 11 715 715, right? Because you added the ligand atoms here, so this number will change. This is the total number of atoms in the system right now. So semicolon and WQ, save and quit. Now we have completed adding ligand atoms into the protein atoms. Next step is updating the topology file also for the ligand, because still in the first step topology file was generated. This topology file was generated, but it was only for the protein. For the ligand we need to include some information. Remember the force field, the ligand ITP file from Swiss param we downloaded. We need to add this one, and in the molecule section of that topology file there were only protein file earlier. Now we will be adding this ligand information there, correct? So I'll go to topology file and just under, remember, so insert mode, just under this uh, I'll put one if you use this semicolon it won't read the flag, so just include the ligand uh, ligand pursuit params, right? So this is for your information. Otherwise you can directly start with include space in the double quotes. You have to put the name of the ITP file which is present in your directory, that is this one, right? So we need to name this one, that is ligand dot ITP, correct? So we have here included, so you can go and check for, so this is uh, the flag or comment which we added to the ligand topology file, right? So I'll go to the bottom of this file and insert some other important things. First one is the position restraint. So I haven't generated it yet, but we'll be generating in some of the step down there, maybe during the equilibration. Oh yes, this one. So we'll be using this flag. Uh, so I can just copy it and generate the restraints right away. This is needed for the equilibration where we want to stabilize our protein ligand complex. So the file will be position restraint underscore ligand. So I'll put this name. So you need to include this comment here for the ligand. Currently this is for the uh, this is only for the protein, right? So I'll just paste it here. Being very lazy, so just change this name to the one which is provided here, that is position restraint. Remember that exact name has to be there, underscore ligand.itp, ligand.itp. So I have included the position restraint for the ligand also. I'll go down and add the information of the ligand. So remember the molecule name was lig in that ligand file. It's not ligand. So there is only one molecule for this ligand. So I'll put one molecule here. So now three things which we modified is on the top was the force field for the ligand, that is this flag. Second thing is adding the molecule section, lig 2. And thirdly, position restraint for our ligand, correct? So I'll put WQ, all right. So now what we have done is corrected the we have generated the complex for the protein and ligand. So let's see. No, this actually is specified for charm force field only. For this demo, we have used only charm. But the link which we have, which I have provided in this tutorial, it will give you the information of um, other force field. There are several servers and programs available. Even some scripts are available where you can convert your uh, files to other force field type files, right? So basically all the steps will be similar what we are doing for other force fields also. Just initially you have to select the correct one and the ligand parameters to be matching with the atom types of that force field. That is the only difference, right? Okay, so now we have successfully built the complex where we added the atoms for ligand and updated the topology file, right? So next is the generation of simulation box. So basically, let's understand this command. We'll be engaging edit conf, gmx edit conf program. -f is input. So remember the input file from the previous step is the input, output file from the previous step is the input for the next step in Gromacs. So every time if you are generating this output file here, that is protein.boxgrow, you'll be using that as an input for the next step. And if you're obtaining this as output for this one, next one, this will be the input for that step, right? So then input will be the previous coordinate file. Output will be the next box coordinate file. And by BT, you can basically specify what type of box we want to select. There are different types of boxes which are available. We have cubic, we have rectangular, we have dodecahedron, octagonal. So basically dodecahedron is very efficient, that less number of water molecules will be obtained. It is roughly spherical. So that's why it is used in this case. You can go with cubic also or other type of boxes also. So -C will put your protein that you are inputting right in the middle of that box, correct? So if you remember, we had seen this one. So it will hypothetically, it will define a box and put your protein right at the center of this protein, correct? So, and then -D and this 1 angstrom is the distance of this protein from the edge of this box. So this is, you can define this one as according to the need. So by default, it is 1 in this case. So I'll just copy this command and just paste it in here. See what happens. So here are the dimension of the box. In some cases, you need to save them, and basically it will give you the diameter, size, and volume of the box, how much is the volume, and some information. So now we have the box, right, and the protein, nothing else. So these waters and ions we need to add later. So next step is solvating the system. So I will use this gmx solvate command now. This is the program which will take the box input from the previous output and will specify SPC row file that is inbuilt in the Gromacs. So it will take the coordinate of water molecules from this file, and output will be the Gromacs solvate file, right? And remember, you need to update the topology from now onwards in every step, correct? So I'll just copy this file and paste this command here. All right. So this is successful. You can see volume is this much, density of your molecules is this much, and number of solvent molecules which are added to the file is 25,441 water molecules have been added. To confirm this thing, whether these are added or not, because we updated the topology here, we'll check the topology again. So go to the bottom, and now previously you remember there was protein, and then we manually added this ligand, built the complex, and now after solvating we have a section which is solved, and it has exact same number of atoms which we are discussing. That is 25,441 solvent molecules. Exact this number, right? That means this step is successful. Now we need to add ions. So in this case, we need to produce the TPR file, that is the binary file for the simulations, and we need to engage this Grom PP program, right? So we will need this ions MDP file, which I had already copied, if you remember, this one. So this is nothing but it gives you some informations about the parameters here. So this ion MDP, and then this is the input from previous output, right? And again, update the topology, and output ions TPR will prepare this TPR file. So just copy this one and paste. Okay, so this may take some time because it will calculate how much uh, is the charge, and how much we need, how many atoms we need to add there. So just calculating. My system is very slow. If you're using a configuration system, so it will not take time. I'm using my laptop, so it's slow. Okay, so let's understand by the time that what is the next step. So next step is gen ion. That means we need to generate ions. How many, right? So this TPR file comes from here, input, and then output will be the protein ion grow. And this is the topology we need to add. Then P name Na means we are adding sodium. N name Cl is we are adding chloride ions. Basically, NaCl salt is used to neutralize the system. And then you have the neutral flag to neutralize the whole system. So basically, it automatically calculates, um, automatically adds, if you use this neutral flag, all the ions, but you can manually. Sometimes we need high, varying concentration of different ions. In that case, you can use manually. You can remove the neutral flag and add the solvents, ions manually. So here you can see that we have obtained one note, that is system is having a total net charge of -16. That means we have to add positive 16 ions, and that is 16 sodium atoms. So I'll run the next command and see what happens. It will ask me, will try to add 16 sodium ions and 0 chloride ions, because already the charge is -16. So we need to replace it with the some of the atoms in the system, and ideally you should be replacing them with this solvent atoms, that is water molecules will be replaced, because every volume is occupied by water right now. So we will replace with 15, that is water. Hit enter and it will tell you which atom has been replaced. So just to confirm, I will go and again check my topology file, and we'll see now that these number of atoms, that is sodium 16, have been added, and the number has decreased previously, right? It was 441, so it has decreased by 16. The solvent is 425 now, and the sodium have been added here. That means the system has neutralized, correct? So next is, now our system is ready. It is solvated, right? It is having the box is generated, solvents are added, neutralization atoms are added. Now we need to minimize the energy, because we have randomly added these ions. We need to minimize the energy of the system. So we'll go with this command. It will engage the GROMPP, right? And then using this MDP file format, which is the parameter file for energy minimization molecular dynamics parameter file. So energy minimization will be done according to this MDP file, and -C is the flag for input of the previous step output file. Topology will be updated, and TPR for this particular step file will be obtained. All right, so I will paste it here and click this one. And then this is the GMX MD run. Basically, to run this energy minimization, it will require this command, that is GMX MD run is the program. And by default uh, parameters, you are running this energy minimization step. And -V flag is for verbose. You want to see what is happening in there. So it is taking some time. So let's understand what is there in the energy minimization MDP file. So I'll open this one. So here you can see the minimization. This is the title. So important thing is the integrator, that is choosing which algorithm which we are using here. So there are several algorithms which are there, such as steep means we are choosing steep here. In this case, that is steepest descent minimization. There are Newton-Raphson, there are conjugate gradient methods, and so on. In this case, steepest descent is used. And this is the energy cutoff that if it goes above that threshold, you need to stop. And these are the steps, energy steps, and the total number of steps which will be uh, used. And these are the other parameters regarding the simulations, and basically cutoff of van der Waals and electrostatic interactions. These are the cutoffs. So be careful while defining these parameters. And one important thing is everything is happening under periodic boundary conditions. So this is nothing but defining a box, right? And making it infinite, because when we simulate this thing, it will go and may hit to the edge. To avoid that edge effects, they do something called as periodic boundary conditions. So if your protein is moving in this direction and coming out of the box, it will be entering from the other phase. If it is going out from here, it will enter from the down. That means continuous motion will be there, but hypothetically, it will not touch any edge of the system for periodic boundary conditions. So this has finished, and now we can run this default command paste. So it may take 10 or 15 minutes more. Sorry about that. So this will take definitely more and more time in my case, because it will neutralize the system. I'll tell you what are the output of this file. Now I will navigate to the other folder here, and we'll try to open this in the terminal. Okay, so this terminal, that is, go to that folder. I have all these files here, right? So basically, what this step will generate is some output files, and one file will be energy file, right? So this EMDR file will be generated of this step, and we can engage this energy GMX energy program, input the energy file, and put everything into this output file, that is potential energy.xvg. So simply putting this command, it will produce you the potential energy xvg file. I have already produced this file, and you can see it through xmgrace, which is one program to see or plot this file, which is for this one. So basically we want to see how the energy of the system has been minimized. I'll try to find out if my file is there. Yes, it is there. So I will simply xmgrace space potential .xvg and hit enter. So now you can see this plot has been obtained. Correct. So this means this is the energy on this axis, and this is the time period for which it was simulated, or steps. So here you can see this graph is coming down like this, and reaches some sort of saturation. That means energy of the system has lowered down, and it doesn't change significantly or doesn't go out of the threshold. So it will stop here, right? That means your system has been minimized. So next is once you complete this step, you have to equilibrate the system. And by using all these commands, now you understand that how you are going to use different commands. So maybe this will never finish. So I will just close this one. So another important step is that you can make a index file for your system. Here you need to define protein and ligand complexes separately, right? So protein and ligand complexes separately because by default, the system doesn't recognize the ligand, which is the molecule which we inserted from outside, correct? So it's not okay. It's not responding. So I'll hit enter. Sorry about that. We need to engage maybe the EM file here, but this will not be produced, so it's difficult to show you here. Maybe I can show you it here. So enter. Okay, so this thing appears, and now you can see there is no protein and ligand complex, but we may need this protein and ligand complex together. So there are some controls for this, for forming this um, index file. So what I'll do is choose one, right? And I will add this bar here. That means we'll put my system together for this one and 13, that is my ligand, right? 13. Hit enter, and now you can see another section has been added, that is protein and ligand. I can view this one here. 22nd section has been added, protein ligand. So we will need this section for the analysis, so we can do that later. So Q is save and quit in this case, so it will form that file, right? Okay, so in the similar fashion, you can proceed with the equilibration step. All the commands are mentioned here for NVT, right? This is the command again, engaging Grom PP, and by checking the energy. So we can basically check this uh, temperature file from NVT, that will be the output. So this is the temperature which we set in this case. So if you want to see the parameters, NVT basically corresponds to stationary number of atoms, volume, and temperature. So basically we put the temperature, reference temperature, as 300 Kelvin in this case, which correspond to room temperature. So this is the one. And here is important thing that you can change the number of step in order to simulate. So basically copy this thing and multiply by this number, that is dt. This is important for setting the time. So I'll copy this number and multiply it by 0.002, that is time step. It will give me 500. This number is in picosecond. So this will simulate your system for 500 picosecond. If you want to simulate it for 1 nanosecond, you will just double this number. That means here you will, in place of 25, you put 50. If you put 100, it will simulate for 2 nanosecond and so on. So you can get that idea how you can change the times. And similarly for NPT, if you see, this one is for 1000, that is 50. 5 lakh. So this has been changed. And here down there somewhere you need to check the groups for which the energies will be calculated. This is protein ligand, which comes from the index which we added, and water ions, which was a default group there, right? Right. And then you can proceed with, so NPT, let's see what is in NPT. So after completion of NPT ensemble, you will get this type of graph. So this is showing very high fluctuation, which is very generally observed situation in case of NPT equilibration, but everything is around 0 and 1. That means we are maintaining atmospheric pressure of 1 Pascal. So next is running the simulations, production run. So again, it will use MDP file. All things will be same. And depending on the time which you put in the MD file, it will take the simulation time. Means completion of the simulation will take that much time, right? Okay, so similarly, after generating this uh, production run, you need to generate something called as XTC file. By default, there will be one XTC file. Sometimes you need to remove the PBC by using different flags, and just for the visualization purpose. So I will quickly go to VMD and will show you the final production which has happened. So I have my files copied here. Seems my system is unable to take that much load. Sorry about that. Yeah, it's opened. So now I'll see the control file, that is this one. So basically I can import or browse the file. From this section, I'll go with md.grow. md.grow, this is the coordinate file which I want to load. Okay, this one you can see this is the file which has been loaded. So I will go and click on this section and load the data into molecule, browse again, and will load the trajectory or XTC file which is generated. That is this one, traject out in this case, and load it. So you'll see the things which are moving. That means it is loading the frames. Here you can see number of frames which are being loaded right now into the system. So I'll turn on the graphics meanwhile. And all protein, if I put, you can create replications and type in all protein. It will show only the protein molecule. And if I want to change to new ribbons, so I can change that maybe new cartoon molecule. So this is the protein. It is still loading the trajectories there. So I can create another application which all not protein, where I can put all not protein. So this will show me how to show it in the lines. So here you'll see the protein, and somewhere you'll see the ligand in there. Right? So yeah, maybe not waters. Remove the waters as well from, and not waters. So only ligands and some of the ligands, other things will be shown. So only protein and ligand complex here you can see. So I will go and change ligands to liability and maybe change my ligand color to some beautiful color ID, maybe some orange. Yeah. So now you can see the dynamic behavior of this protein and ligand binding. So in this case, you can see the ligand is tightly bound to the protein, and this is the quality of a good inhibitor, right? So it is tightly bound to the active site. If it is not binding tightly, the inhibitor will jump off this binding site and will go into the solution. So that can happen and may lose important interactions during the simulation process. So this is about the visualization. Apart from that, you can calculate other parameters such as RMSD, RMSF, and radius of gyration by using this MDTPR file, which will be obtained from the last production run. And choosing these output files, you can plot it with help of XMGrace to obtain the final results, something like this RMSD and radius of gyration. So I hope that's all from my side. So let's see if there are some questions. And so this was answered. Can we change the temperature and run the MD? Of course, you can change the temperature because the parameter file, it allows you to set any temperatures, right? So there are so many variations you can do, and all they correspond to the parameter files. Based on the parameter files, the simulations will run. Yes, you can change the temperature. So any other questions, please? You can speak out if you
Good
want.
evening, sir.
Yes, please.
Sir, I was running a simulation for protein only, basically.
All right.
So, sir, in that I was going for secondary structure analysis through Gromacs DSSP command.
All right.
And there I was generating, like I was bound to generate a dart extension file because earlier by do DSSP it was generating XPM file, but now it is not allowing to generate that file. Can you please suggest how can I just get that XPM file from the dart file?
Oh, so I need to check that out. I'll note it. What did you tell? That is dot dat file to dot STF file,
STF, no sir, XPM.
XPM file. Okay, I need to check it. It's
Okay, sir.
been a while I have used that. So is it the problem like you can't plot that dat file?
Sir, actually, earlier it's like it is giving a colorful pictorial representation of the secondary structure where it was showing all the helix and all the like sheets
Yes.
along with the nanosecond scale.
That
But
is with the dat file, right?
no, no, sir, that is with the XPM file.
Okay.
While we are using do underscore DSSP command earlier version.
Okay.
But now, as they are updated and they are not allowing that particular command, they are only allowing DSSP command. In
Yeah,
that,
it will be DSSP. So, okay, just quickly, I will guide you to because we need to construct our commands according to our needs. So I'll just try to see what is in there. So always you can go to the help of GMX DSSP. So this is online, um, what do you say, online user manual. So you
okay.
can check for the options here, right? Okay, here.
Yep,
So
sir, for
can you
output
see?
only. Yes,
So
sir.
if you put this output
Hmm.
and name some output.dat, it will give you the
Hmm.
dat file, correct?
Yes, sir. I
So,
got this file, but the problem is I'm not that is not in a readable form.
okay, so you need to convert it to XPM.
XPM
So,
or any of readable forms.
yeah, so I have to check it again. Did you check the web for some help? Because in here,
Yes, sir, but
output is
I'm
only
not
dat file.
actually getting whatever online tutorial is present, like for conversion. They are
Okay,
not able to convert it.
so can you please send me an email? I will reply if I find a solution for that. Okay,
Sure, sir,
because
sure. I will
recently
just,
I haven't used this command. Sorry about that.
okay.
So I'll find the solution for you.
Surely, sir, I will mail you in the mail ID you have provided yesterday.
Sure.
Thank you so much.
So any other question?